Now let's go ahead and find the least squares regression line for this following data. First of all, we want to go to our calculators. We want to go to Stat and enter our data. So hit Stat and then enter and edit. If you already had data in here you want to get rid of it, remember you want to arrow up and hit clear and then hit enter. You're going to type in the first number of each parenthesis, the 2, the 5, the 1, the 8, and the 6 into your first list. Then arrow over to the second list and type in the second number, the 4, the 7, the 5, the 10, and the 8. To find the line of best fit, or the least squares regression line, you then want to go Stat, arrow to the right to Calc, and then go down to number 8. And then hit enter on number 8. Your calculator then gives you this. You then want to go ahead and substitute in the value of A and substitute in the value of B. And then write your equation. And so then you would go y hat, replacing your A value with the 3.301, replacing your B value with what B is, and then plug in X. Now, if this was done in the context of a real-world situation rather than just points, you would then also have to say X is representing blah, and Y is representing blah, blah. So you need to actually tell me what X and Y are representing in the context of your problem. In this case, we were just dealing with numbers and there was no context, so we don't have to do that. Now, let's take a look at the effect of outliers and influential points. An outlier is an observation that's significantly different than the overall pattern. Now, here we have an outlier, you might say is child 19. It's significantly higher than all the other points. We also have an outlier in the horizontal direction, which is 18. However, we would say 18 is not an outlier in the context of the problem. Yes, it's significantly different, but it is still pretty close in line with what we would expect with our least squares regression line. So we would consider 18 to be an influential point. Yes, it's off to the side, but it's really still pretty close to our line. But if you have a point that's vertically up and down significantly different than all the other points, then we would consider that an outlier. If it's pretty much in line with your line, then it's an influential point. Now, looking at that last graph, here we have three lines. We have the black line, what it would be without child 19. We have the solid maroon line, what it is with all the values, and then we have the dotted line, what it would be with all the values except for child 18. And you can see how with child 18 it's significantly different than what it is without it, and so we would consider it to be influential. Keep in mind, if you're dealing with averages, averages are spread out less, so therefore you typically end up getting a higher R in R squared when you are dealing with averages. Now let's go ahead and make predictions using our least squares regression line, which is interpolation. And interpolation is what happens when you make predictions within the range of your data. And you only want to make predictions within the range of your data. Here our data goes from 1 all the way up to 8. So we would not really want to make predictions beyond the value of 8 number of beers. So let's go ahead. Here's our least squares regression line. Let's make a prediction for 6.5 beers. If we do that, we want to take 6.5 and plug it in here for x. So we're going to go 0.0144 times 6.5 plus 0.0008. And that's what we were doing down here. And when you type that into your calculator, you end up getting this. And that would be your blood alcohol level measured in the units that you were given on your graph, which is right here. So whenever you're making predictions, you just plug it into your least squares regression line. So, taking a look here, here we have our motorboats, and we're dealing with number of deaths of manatees based on the number of motorboats, and notice it's in thousands. If you do a scatter plot, it looks like this, and I would say, as you look at your data, yes, it does look fairly linear, so a least squares regression line would be appropriate. So, when you do your least squares regression line, you get this one right here. Now, we want to go ahead and make a prediction. Using your least squares regression line right here, we want to know if you have $500,000 or 500,000 motorboats, how many deaths can we expect? Well, keep in mind this is in thousands, so that's really 500,000. So we're going to use 500 in here. So we're going to go and plug in 500 for our value of x. And now all we have to do is just go ahead and type that into our calculator. And we would get, say, 21.1. Well, we can't have part of a manatee, so we're going to just go ahead and say it's roughly 21 manatees we would expect to die with 500,000 powerboats down in Florida. Now, when you're dealing with regressions, you want to make sure that you're looking at your residual pattern because you want your residuals for the most part to be a random distribution of points. If there's any patterns where it's above or below significantly, then you know you have a bad linear regression, and it's probably not linear. You want to be aware of outliers. You want to be aware of clumped points. Also be aware when you're using averages, and just be aware that whenever you're dealing with a strong relationship, not necessarily one implies the other, or there's no causation. And beware of lurking variables. And then you never want to extrapolate. Extrapolating is when you're trying to make predictions beyond the range of your data. So let's talk about lurking variables here. Lurking variables are basically affecting your results and may give you false relationships. It's something that wasn't really considered when you were comparing your data. So let's go down here and take a look at this. There's a strong relationship between the number of firefighters at a scene and the amount of damage a fire does. So does that mean increasing the firefighters causes it to be a worse fire? No. It's really the size of the fire is your lurking variable. At a large fire, you're going to end up getting more firefighters to show up to fight it. And hence, because it's a large fire, you're going to have more damage. Also, there's a negative association between the moderate amounts of wine being drunk and the death rates by heart disease in developing nations. So in other words, the more wine that's drank in a developing nation, the lower the death rates by heart disease is. Well, the lurking variable here is that for the most part, wine is not a poor man's drink. And so if they're drinking wine, the country overall is a better standard of living. And if you have a better standard of living, you have better health care. When you are comparing the age of boys from like 3 through 17 to their height in inches, on average it looks like this here. It's fairly linear. Now, you may want to say, well, what would be the predicted value at age 24 or at the age 33? Well, at age 33, you go straight up to your line, and then you go straight over here, and you'd be at 110 to 115 inches tall. But we know that that does not make sense because we know once we hit around the age of 18, we don't grow nearly as much. And then eventually we stop growing. And so that's an example of extrapolation, going and making a prediction beyond the range of your data. You never want to do that. Down here you see as you're plotting your data, it levels off. So only make predictions within the range of your data. Never go beyond the range or scope of your data. Now the Y-intercept, as we are looking at the Y-intercept where it crosses your Y-axis here, it would be a negative, and we know we can't have a negative blood alcohol level. It makes no sense in reality. However, in the context of your equation for the line that best fits your data, it is acceptable and appropriate to use a negative Y-intercept. So now let's take a look at these sets of data. You want to always go ahead and plot your data. Each one of these four sets has a least squares regression line of 3 plus 1/2 x. So if you wanted to make a prediction, and they all have the same R value, if you wanted to make a prediction of x being 10, you plug in 10, half of 10 is 5, plus 3 is you would get 8. But that does not make sense with all these. You always want to make sure you plot your data. Plot your data first, and then look at it. As you look here, you'll realize that the first set of data, it would be pretty good to use in least squares regression line because it's kind of randomly distributed on each side of your line. However, in B, there's a definite curve pattern. And your least squares regression line does not work for curved relationships. In example C, you have a definite outlier. Since you have a definite outlier, you would not want to use your least squares regression line. Or in D, you have some clustered points down here with one significantly different point, so that would be another example where you would not want to use your least squares regression line. So always plot your data and only use your least squares regression line and make predictions in an appropriate set of data where it's randomly distributed on either side of your line. Now, just because two things are associated does not mean one causes the other. Here's a couple of examples. As you get larger shoe sizes, your reading level increases. So does that mean if you have big feet, you're a better reader? No, it does not. There's some lurking variables going on here. The lurking variable over here would be the context of age. The older the child is, the larger their shoe size. And the older the child is, on average, they can read better. So that's your lurking variable. So your shoe size does not cause you to read better. Is there a relationship, an association here? Yes, but one does not cause the other. Also, you can see over time, as time increases, the infant mortality rate is going down. Now, just because your time increases, does it mean it's automatically going to go down? No. The lurking variable here is that as time increases, so does technology, and better technology and better information allows you to have a lower infant mortality rate. So that would be your lurking variable. Lurking variables are among the explanatory and response variables that are not being studied. So they influence your results, but you did not collect data on those. Confounding variables affect the response and cannot be distinguished from each other. Now, your confounding variables may be lurking, or they may be an explanatory variable. They are often used interchangeably, the lurking and the confounding. However, if you are taking a quiz and you're not sure if it's a lurking or a confounding, there's only going to be one of those two words available for you to choose from. I'm not going to put them both in the same question and have you choose between them.